One thing that's often either overlooked or just not focused on too much in chemistry, especially general chemistry, is that most reactions aren't simply a matter of two reactants coming together and giving you your products. A lot of time there's some things going on between the reactant stage and the product stage. And like I said, most cases those are either just ignored or just not concerned with them. But when you're looking at rates and studying the rates of reactions, the in-between stuff can be pretty important. For example, with nitrogen monoxide and oxygen coming together to form NO2. One possible thing that can occur here is that one nitrogen monoxide and one oxygen can come together to form NO3. And this is what we'd call an intermediate. It's an intermediate because the NO3 can go on and react with another equivalent of NO to give you NO2. If you notice the overall reaction, if you add these two equations together, like you would if you were adding two algebra equations together, the NO3 effectively cancels out of the equation, and you're left with two NOs plus O2 gives you two NO2s. So this two-step process where you form an intermediate NO3 and it goes on to form NO2 is what's referred to as a mechanism. A mechanism tries to explain how a reaction goes from reactant to product. Sometimes you can't have a one-step mechanism. Sometimes it can be two steps, three or more. Depends on the reaction. So chances are these two steps in the mechanism aren't going to occur at the same rate or speed. One of them is probably going to be relatively slower than the other. And in most Gen Chem textbooks and most Gen Chem courses, instead of giving you any kind of rate data, you're just simply told, which one is slow and which one's relatively faster. And the slow step of a mechanism is what we call the rate determining step. It's the step that basically determines the overall rate, or it has the most influence on the overall rate of this reaction as you go from the first step down to the last step. Now when we look at the overall reaction, the rate law of an overall reaction can't be determined just by looking at the coefficients, mainly because you don't know what's going on in between reactant and product. But for a single step in a mechanism, the rate of a step is equal to a rate constant times the concentrations of your reactants. And the exponent for each concentration does come directly from the coefficients, mainly because there is no in-between. This is one single step. So if this is the rate law of the rate determining step, and if this step has the most impact on an overall reaction, what you should see is that the experimental rate law should equal the rate law of the rate determining step. In other words, when you experimentally determine the rate law of, say, this reaction, if this is a possible mechanism, then it should be first order with respect to NO and first order with respect to oxygen. If your experimental data doesn't agree with the rate law for this the rate determining step of this mechanism, then this mechanism isn't going to work. It can't be a possible mechanism for that reaction.